Hello children, now the chapter 6, work, energy and power. That we'll see before we are going to know about what is work, energy and the power. What is dot product, or we can call it as a scalar product. We are going to recall it. Already we have studied in that previous chapter, right? See, the dot product, the symbol of multiplication between the vectors is represented by the dot, and the result of the product is the scalar value, right? So if we consider two vector A and B, if suppose it is making an angle theta with each other, the dot or the scalar product which is given by A dot B, that is A vector dot B vector, which is equal to modulus of A vector modulus of B vector cos theta. Or we can say cos theta, which is equal to what? Then A vector dot B vector whole divided by modulus of A into modulus of B. Or we can say A vector dot B vector, which is equal to A into, that is A of A on B cos theta for this case. Or we can say A vector dot B vector B on A cos theta, right? So the two different cases which is saying geometrically B cos theta is the projection of B onto A, and A cos theta is the projection of A onto B. Understand? Now we'll see the properties. See, the dot product results in a scalar value, and the scalar product is commutative in nature, so that A vector dot B vector, which is equal to B vector dot A vector. So that is the commutative property it will come under, and it is a distributive property also. So A vector dot B vector plus C vector, which is equal to A vector dot B vector plus A vector dot C vector. And also we know that the dot product of I dot I, J dot J, K dot K, which is equal to 1. And I dot J, J dot K, K dot I, which means that is equal to 0, right? I dot I means 1. I dot J means that is equal to 0. Then the component of A along B, that is equal to modulus of A cos theta, that is equal to A vector dot B cap. Understood? And in the same way you have to take it for the component of B vector along A vector. So these are all the properties of dot product. Okay. So these are all we have studied in the previous. Also you must know before we start the work energy. Now we'll see what is work. Okay. The work, which is nothing but we can say the work to be done whenever a force acts on a body and the body moves through some distance in the direction of the force. We'll explain in next slides also these things. And work done on a body only by following conditions, that is, it must satisfy a force act on the body. The second thing, the point of application of the force moves in the direction of force, right? For example, a man, suppose climbing a stairs, we can say does work. Some work has done by the person. A horse pulling a cart does work, right? So we'll see in detail. Suppose through some of the examples we can understand. Here an engine move or moving vehicle does work. Is it right? And we can say that a body which is dropped from height falls downward the earth. So towards the earth, it indicates that the earth exerts a force of attraction on the body. The gravitational force does work in pulling the body towards it. So from the above explanation, we can understand that the work is said to be done scientifically. We must know when a force which is applied on a body produces motion in it, right? So we can now satisfy the two conditions, that is the work done by the force, it is defined as the product of component of the force in the direction of the displacement, right, and the magnitude of this displacement. Work done then which is equal to component of force, that is force into displacement. So F into cos theta, F cos theta into S. So F is cos theta. Work done which is equal to F cos theta S. So we can give here the scalar product, that is W, which is equal to F dot S, F vector dot S vector. Work done by a parallel force, we can see now. See, if suppose we have taken the force F displaces a body through a distance, yes, that is parallel to the line of action, right? It is parallel, right? The force which it gives in the same direction and also it is parallel. So the force, or we can say in the direction of force. So from this example we may understand that the work done which is equal to, as per the definition, force into distance moved in the direction of force, or we can say displacement, right? So W which is equal to Fs cos theta. Here that is moves in the parallel. So cos 0. So W which is equal to Fs. Now work done by an oblique force. So if suppose it makes an angle. So now we are measuring the work done when the force and the displacement are inclined. See, both are inclined in nature now. So the work done is what? We have to take component of force in the direction of displacement into the magnitude of the displacement. So that the W which is equal to F cos theta into S. So F cos theta into S we have taken. So Fs cos theta. Got it. So W which is equal to F dot S. And also we'll see that how it is resolving with the help of two components, that is x-axis and the y-axis, both we have taken. So the vertical and the horizontal both we have taken, f sin theta and f cos theta. So f sin theta which is acting in the vertical direction, it does not displace the body in the direction, right? Therefore the work done by the component f sin theta is 0, whereas we have taken that f cos theta which is acting on the horizontal direction, it displaces the body in the direction. So that we have taken the work done which is equal to force into displacement. So W here which is equal to Fs cos theta. Understood? Now, when is work will be 0? When we can say the work is 0? See, for work to be done, both force and displacement must be present in the body. So that is the condition for doing a work. Is it right? See, if a force applied on a body does not produce displacement in the body, means scientifically what work is not done, right? For example, we can see a man holding a book in his hand, right, in a stationary position. It does not do any work since the weight of the body acting on him, it does not produce any displacement. Whereas a man trying to push a rigid and stationary wall does not do work since when a force applied by him does not move the wall. Is it right? So this time we can say that the work is 0 here. If a force applied on the body, it does not produce some displacement in the body. So that we are concluding that the work is not done by the person in these two cases. Understand that. Now, some of the points we can see that. So what we see, work is a scalar quantity. It has the dot product, that is W which is equal to F vector dot S vector. Is it right? W which is equal to Fs cos theta. We have seen. So work can be positive, 0, and it will be negative. So negative work does not mean in a vector quantity. The work done by the friction is negative. It is in the opposite direction of the displacement. We'll see in the upcoming classes, right? The dimension of the work, right? M L square T power minus 2. We have to take it from the work formula itself, right? SI unit of work is joule and it is a scalar quantity as we said. So 1 joule which is equal to 1 Newton into 1 meter. That means what? 1 joule is the amount of work done when 1 Newton of work acting on the body displaces it through 1 meter. And 1 joule which is equal to 10 power 7 ERG. CJ's unit we have to say ERG, right? Erg. 1 erg which is equal to 10 power minus 7 joule. Right. So these are all the points you must know. Now, what is positive, zero and the negative work? That we can say that the nature of work done in different situations, right? It may be like, if suppose we are saying although the work done is a scalar quantity, but the value may be positive, negative and zero. Now we'll see. For first case, we will take the positive work. If a force acting on a body has a component in the direction of the displacement, then we can say the work done by the force is positive. Understand? So, W which is equal to Fs cos theta, that is equal to positive value. So, theta which is less than 90 degree. Is it right? We can say some examples like when a body falls freely under the gravity, that time theta which is equal to 0 degree. Then we can say the work done by the gravity is positive. Understand, this is positive, the positive work. Next one we can see that zero work. See, the work done by the force is 0, which means what? The body gets displaced along a direction, perpendicular direction of the applied force. So we can say the work done is 0 because F or S both are 0 here because theta is 90 degree. See, for example, we can take the same case. If suppose a body moving in a circular path, the centripetal force and the displacement are what? Perpendicular to each other, right? So the work done by the centripetal force is what here? 0, right? So W which is equal to Fs cos 90. So W which is equal to 0 here. The third case, the work done is negative. If a force acting on the body has a component in the opposite direction of displacement, direction only gets varied. You have to understand that. It is not a vector component. Direction is varied. It is not in the same direction of force. Right. So now we can say the work done is negative. Right. So when a body suppose slides against a rough horizontal surface means what will happen? Its displacement is opposite to the force of friction. So now we can say for this case, the work done by the friction is negative. For example, one more example I'll explain that. When brakes are applied to a moving vehicle, the work done by the braking force is what? Negative. So this is because of the braking force and the displacement act opposite direction, right? So W which is equal to minus Fs. So that's it, children. Thank you, children.